First off, the term for stress, as is given in this diagram, can be given as related to the force divided by the area. And we'll describe that right here. The units we see for stress, the SI unit is pascals, abbreviated as big P, little a, and it's related to newtons per meter squared. It's the unit that's related to pounds per square inch, pounds force per square inch, which is the English version of this unit. Now, often, the magnitude of stress that we see, newtons per meter squared, is not such a great deal of stress, and so in many cases for material science applications, we'll be looking at stresses that are a little bit higher. In fact, we'll be looking often at stresses which are described in terms of MPa, big M, big P, little a, which is 10 to the 6th pascals, or we'll be talking about gigapascals, which is 10 to the 9th pascals. Many of the stresses we apply for deformation of materials, and I'll abbreviate deformation as DEF and a little n, okay, fall into this range, and the magnitude of many of the room temperature elastic constants for conventional materials fall into this range. So we'll be seeing MPa and GPa quite often, or megapascals and gigapascals. So let's look at the different types of stress. Just like strain, we can describe stress in terms of both an engineering value and a true value, as is shown here. So we have the engineering stress, we have the engineering stress, which is defined as shown here. And we'll get this term on here. So engineering stress is shown here with ENG, and it's related to force per unit area, but in this case the area is the initial or the nominal area. So it doesn't evolve or change with the force that's applied. This particular case, the true stress, actually allows for the instantaneous area. So it's the instantaneous or the true area. Okay. If we assume constant volume, these two stresses can be related to one another just simply by multiplying the engineering stress by 1 plus the engineering strain. Straightforwardly, that is the definition of the relationship between the two. And it does rely on the assumption of constant volume, which it turns out is not true that often. Plane stress is defined here. So what is a plane stress? A plane stress is a situation in which all the stresses are confined to one plane. That means that there are no forces or corresponding stresses in or parallel to one of the axes. So let's define a set of axes in order to describe what we're going to do here. So we'll take X, we'll take Y, and we're going to describe a stress. So we're going to describe first off this stress, sigma 1, 1. Sigma 1, 1 is a stress that corresponds to a force, and we can see this is defined over here. It'll be a force in the one direction on a face, if we make the J match here, on an area. And the way the area is defined is an area is the area perpendicular to that axis. So if we look at this area and we apply a force normal to it, so this area is A1, this is F1. If we also apply the negative of that force, because we need a force couple in order to define the stress, so this is also F1, but it's F1 pointing in the minus direction, and it's on a face that is the negative face. It's actually the face that points